there's a couple of other techniques that I want to expose you to this hour of class that involve trig identities. And so here's our first example. We have the integral of sine cubed x dx. All right, so when I look at this problem up here, the very first thing that I might do is say, okay, sine functions have that shorthand way of writing powers, but really what this is sine of x quantity cubed dx. And then I look at this and say, okay, I do not know an antiderivative for sine cubed x or for sine of x quantity cubed. So my first thought is I see an inside function, which is sine x, and an outside function, which is x cubed. And so because of this composition of functions, I might try a u sub. And so my first idea might be to say, let's let u be equal to sine x. And so in doing this, I end up with du over dx is equal to cosine x. And I solve for dx, and I end up with du over cosine x. All right, so I'm a little bit sad about this because suddenly I'm going to have a cosine of x pop up in my problem, but based on our last example, I'm going to keep going a little bit and see if I can do some work on some cleverness. So here we go. We've got our integral. We have sine of x cubed. Well, u is sine x, so we really have u to the third. And then we have dx, which we replace with du over cosine x. And at this point, I'm very sad because I really see absolutely no way to get rid of this cosine x. And so I have a mixed integral. And so because I have both x's and u's involved, there's not much I can do with it. So I'm going to be a little bit sad here. And I'm going to at least put this on pause and possibly not go any farther with it at all. Okay? So because we have this cosine of x in the bottom, life is not so good. Okay, so I go back to the drawing board, and by the way, this happens a lot in analyzing integrals, this idea of trying something out and maybe it doesn't quite work, so we go back to the drawing board. And so I write down my problem again. And so this is attempt number 2. So I look at the integral of sine cubed x dx. And again, I can think of this as sine of x quantity cubed. And then I think about this u substitution that I'm looking at here. This choice I made over here, when I took the derivative, I ended up with one trig function. It was a cosine function. So when I take the derivative of a single trig function, of a single sine function or a single cosine function, my derivative is also going to be a single function. Which means that in order to get rid of this cosine function down here, I needed a single cosine function on the top. And I didn't have that. Now over here, I can work with this a little bit. I can rewrite this as sine squared x times sine x dx.
That's what I was thinking. Yeah.
And so when I do this, what I see here is a single trig function. And that single trig function is going to help me cancel whatever ends up in my denominator from my dx. And so what I want to ask myself is there a trig function whose derivative is sine of x? Yeah, technically it's negative cosine x, but rather than having to work with the negative signs, those will all come out in the wash, I'm going to choose a u value that is a trig function whose derivative is going to be canceled with this sine x. So my choice for u is going to be cosine x, even though I see no cosines up here in this original problem. So when I do this, then my derivative, du over dx, will be negative sine x. And I solve for dx, so dx is du over negative sine x. And this is making me feel a little bit better, because at this point, I now have the integral of sine squared x times sine x. I didn't have anything to substitute u in for. And my dx would become du over negative sine x.
Sorry, I think I missed something. So you can just choose something, even though it's probably not in the,
Yes, your
Okay.
choice for u can be anything you want it to be.
okay.
The number one big fat rule of thumb is if there's an inside function, we choose that because often the derivative is showing up and it will cancel it. But sometimes that doesn't happen, and here's an example of that.
Well, how come in the first one you can't put a 1 in front of that u cubed as a cosine x over cosine x?
Like this?
Yeah.
Okay, so that's not a bad idea. So now this cosine x will cancel with this one up here, right? But I still have this guy. I still have a 1 over cosine x thing. This guy's still there. But keep thinking about it, because it is certainly possible that we might be able to do something here. But that's still, that route will still leave us with a 1 over cosine x.
On the sine squared x, couldn't you just put that, substitute that in for 1 minus cosine x?
Yeah, so that idea that we tried right before the break, so here we've got our sine x's, they cancel, the negative gets brought out in front, so we've got negative the integral of sine squared x dx, or I'm sorry, du, and again we're a little sad because we still have x's and u's, but that idea that we talked about right before the break, that Pythagorean identity, the one that you want tattooed on your arm, sine squared x plus cosine squared x is equal to 1. We can solve that for sine squared x. So sine squared x is equal to 1 minus cosine squared x. And since our u choice was that u is equal to cosine x, well, 1 minus cosine squared x is the same as 1 minus u squared. So we can make that replacement in our integrand. And so we have negative the integral of 1 minus u squared du. All right, are there any questions up until this point?
So in order to eliminate the negative sign right off the bat, can you just use negative cosine just to get it to be sine when you do the derivative?
So that would also work as well, and so that would make you not worry about that negative sign in front. Now, when you go and look inside, you have to be a little bit careful. I guess because we're squaring here, then the negative, this would be a cosine of x squared would be a negative u quantity squared, which would cancel there as well. You just need to make sure you take that into consideration. Okay.
So, in choosing, like, you know, since we now know that we can use any u value, is there a rule of thumb that we want to try to do? Or, you know, like, in there, like, you canceled your signs out, so we want to know that our derivative, our dx value, will have a sine x on the denominator?
That's exactly right. So your choice for u, what you want to think ahead to is, okay, my derivative is going to have a term in it, and will that term be able to be canceled?
Okay.
And so that's another way you want to say, okay, will my u value give a derivative that can either cancel something in the integrand or allow itself to be canceled itself? Okay, so let's keep going now. At this point, we now have this negative sign out in front. We can take our antiderivative. So we have u minus 1/3 u to the third, and all of that is plus c. And our final step is to replace the u's with cosine of x. So we have negative the quantity cosine x minus 1/3 cosine cubed x plus c. And if I wanted to, I could certainly distribute that negative sign through as well. Not required, but totally legit. All right, so the two things that happened in this problem that were different from what we've seen before. The first one was we made a choice of u that was seen nowhere in the original problem. And so what we saw was, hey, if I have this power to the third, well, I can pull one of those sine functions out and ask myself what u will give me a derivative that will cancel an extra sine x. Because if I have leftover signs to even powers, like sine squared, I can use my Pythagorean identity to make some adjustments in the end, some substitutions. Okay, so some questions that you might be thinking about at this point are, holy crud, this could totally turn into, we're totally opening up a can of worms here. Like, I thought I had U substitution down, and now you're throwing in all these new ideas, and you're using trig identities. Man, I had trig 3 semesters ago, and there were 552 trig identities that I learned in that course. What do I need to know for Calc 2? And the answer to that is, I'm going to give you a list of 4 trig identities that you will find useful over the next few weeks. What trig identities will be useful? And there are 4 of them. The first one is our standard sine squared x plus cosine squared x is equal to 1. Our second one is another Pythagorean identity, the one that looks like tangent squared x plus 1 is equal to secant squared x. I tend to forget this one, but I can always refigure it out by looking at the original one up here, which I have tattooed on my brain, and taking that one and dividing by cosine squared x all the way across, and you get this one right here. Okay, so if you cannot remember the second one, take the first one and divide by cosine squared x. All right, the third one is sine squared x is equal to 1 minus cosine of 2x over 2. And the last one is cosine squared x is equal to 1 plus cosine of 2x over 2. These 4 trig identities you are going to find to be very useful. The first one 100 times more than the others, but those other 3 are running a close tie for second. Okay, so let's take a look at an example that's going to use a slightly different trig identity. And here it is, the integral of sine squared x dx. Alright, so when I look at this, this is really similar to the last problem. The last problem we looked at was sine cubed of x. And what was cool about that sine cube was that when we pulled out one of the sine functions, we were left with a sine squared times one individual sine. So that one individual sine could be canceled with a derivative, and the sine squared we could use our Pythagorean identity, and it was really helpful. Here, I have an even power. And so if I pull a sine function off to the side to cancel with a derivative, I'm not going to be left with a sine raised to an even power. And so this Pythagorean identity is not going to be helpful. So the second that I see an even power up here, an even power on the trig function. Trig function meaning a sine or cosine function. That's specifically what we're focusing on right now. Okay? When I see an even power on a trig function, I want to get rid of that as soon as possible. So if I only see even powers, what I want to do is I want to look at these number 3 and number 4 trig identities. And I call these the lowering power identities. So I'm going to take my sine squared x and I'm going to replace it with 1 minus cosine of 2x over 2. I'm going to use my lowering power trig identity. Alright, so here we go. We've got the integral of sine squared x is 1 minus cosine of 2x over 2, and then I've got my dx at the end. Now, in terms of this whole fraction, that's just a 2 in the denominator, so I can pull that into the front as a constant. So I'm going to write this as 1/2 the integral of 1 minus cosine of 2x dx. Alright, so now I look at this integral, and I say, okay, what am I going to do with this? I now have a trig function raised to a first power, so that's good. The next thing I would say is, okay, what do I want to do next? So I'd like you to turn to one of your neighbors, and ask your neighbor what they would do next.
What would you do?
That way you can get into this one. Trade from there and sort of.
I would say u
What are you doing? And then the 2
So then we plug that back in.
We have all you that though. We have all you
Yup. But there's already, so you would put that in front, so you want 4?
2 out again.
See what I'm saying?
Yeah.
Actually, no, because you still have.
You don't.
So it's there.
So it's still just 1 minus, 1/2.
Okay, so can I have your attention back up here? Anybody, when you asked your neighbor what they would do with this integral, what the next step would be, did anybody have a neighbor who came up with a good idea?
I think we all came up with the same idea.
You all came up with the same idea? Okay, what was your same idea?
U equals 2x.
Okay, so looking at this, what made you decide to use u equals 2x?
It's in the parentheses, I just figured it would be the most best thing.
Alright, so this seems like a totally reasonable idea. So when we look at this integral here, when I analyze this, I see a 1 and I see a cosine of 2x, and they're connected by a subtraction sign. So I can think about finding the antiderivative of 1 and think about finding the antiderivative of cosine of 2x separately. So I know what the antiderivative of 1 is. That one's pretty easy. The other one, though, the cosine of 2x, I know the antiderivative of cosine of plane x, but because there's something fancier inside the parentheses, I want to consider using a u substitution. And the good choice for a u substitution is the 2x, because that's the fancy thing inside the parentheses. Alright, so let's go ahead and work through that. We have du over dx is equal to 2, and so dx is equal to du over 2. Okay, so if we make our substitutions, we've got 1/2 the integral of 1 minus cosine of u, and dx is du over 2.
So you just throw the 2 out, yeah.
Yeah, that 2, this 2 right here, we can bring that right to the front. Remember, it stays in the denominator, so this number in the front becomes 1/4, 1/2 times 1/2. The integral of 1 minus cosine of u du. Okay, so at this point, we have our entire integrand in terms of u. We've got a du at the end, and the things inside, in here, in the integrand, are all easy functions to find antiderivatives of. There's nothing fancy going on there. So we can take our antiderivatives, and so when I do, I've got the antiderivative of 1 is u, because we are taking the antiderivative with respect to u. And then our antiderivative of cosine is positive sine, so we have u minus sine of u. Now we have a plus c at the end. Okay, so final answer is 1/4 times u, which is 2x, so 1/4 times 2x minus sine of 2x. Excuse me, plus the. Alright, are there any questions about that?
Yeah.
Yes,
That's good.
How did you get the second out? Yeah. In your second step,
this one here?
in the second,
Here. Did I have to pull the 1/2 out in the front?
how did you get that?
Oh, how did I get that? So this guy, this 2 was divided into both of these terms. Another way to write this expression in here is that I can write this as 1/2 times the quantity 1 minus cosine of 2x. So by having a 2 in the denominator, dividing by 2 is the same thing as multiplying by 1/2. So
I'm just seeing that one in front of the cosine.
this one here.
Yeah, I'm thinking that should be with the
So maybe another way to see that part is, so if I have 1 minus cosine of 2x over 2, when I divide the 2 into each term, then I have 1/2 minus 1/2 cosine of 2x. So that's another way that I could write this. And what I've done is then factor out the 1/2. And if I factor out a 1/2, then I've got 1/2 times 1 minus cosine of 2x. And so any of these are all legitimate ways to think about writing that down.
On the second board, I'm getting confused between my second, third step. So do you
From here to here.
Yes.
Okay,
You to get like u minus sine u,
yes.
you're like multiplying in the du kind of.
So the integral sign and
Oh,
the
right,
du
right.
together say take the antiderivative.
How do you get the u then?
This u right here.
Yeah.
So if this were, one way to think about it is if you take the derivative of u, its derivative is 1.
Yep.
So if it would have been an x, it would have just been, if it would have been dx, it would have just been x.
Right, so if you had the integral of 1 dx, then your antiderivative is x. Plus.
It's just whatever's on the end of the derivative, right? Or-
Right, that's correct. That's correct. And if this were an 11 dx, then it would be 11x would be your antiderivative. Okay, other questions?
Would you be able to split those up on the second step, so 1/2 times integral of 1 with x minus?
Yes. And so one thing that you want to be careful of when you do that, so what you're suggesting is 1/2 times the integral of 1 dx minus 1/2 times the integral of cosine of 2x dx. So focusing on these as two separate integrals. The first one, you're taking the antiderivative with respect to x. This one, you're going to have to do the u substitution on.
But once you substitute u back in, you can still do the same.
Yes. Yep.
Would it be the same answer?
It should be the same answer. Yep. Check it out and see. If not exactly the same, then only off by a constant.
Just adds a few more steps.
Yeah, so there's advantages and disadvantages. One advantage is that in this case we can cancel, everything cancels nicely. Sometimes it doesn't and you do have to split it up. Alright, other questions or comments? These are all really good questions. Thank you everyone for asking them. These are things that we want to analyze now because you want to sort out those wrinkles now rather than later. Okay, so let's look at another example. The moral of the story on this one is we had an even power, and with an even power, we cannot use that cool little trick of pulling one of the trig functions out. We actually had to use this lower power trig identity. I'm going to leave these identities up over here on the left board.